Somewhere in the depths of space, brighter than 1 trillion suns, lie the most powerful beacons in the universe, quasars. They're so distant that their light began its journey before Earth even existed, traveling for billions of years across the cosmic void just to reach our telescopes today. These mysterious objects shine with such incredible intensity that they outshine entire galaxies containing hundreds of billions of stars. Yet they're no larger than our solar system. What are they really, and what secrets are they sending across the cosmos? Imagine standing in a completely dark room and suddenly seeing a lighthouse beam so bright it illuminates everything for thousands of miles around. That's what quasars are like in the universe. They're cosmic lighthouses broadcasting their existence across distances so vast that human minds can barely comprehend them. When we look at a quasar through our most powerful telescopes, we're not just seeing light, we're seeing a message from the ancient universe, a story written in photons that has been traveling toward us since before our planet was even formed. These aren't just pretty lights in space, they're cosmic time machines, each one carrying information about what the universe was like when it was young, wild, and very different from the peaceful cosmos we see around us today. Picture the universe as a vast ocean, and quasars as the brightest beacons ever created, sending signals across that ocean for billions of years. Some of these signals started their journey when the universe was less than 1 billion years old, when the first galaxies were just beginning to form and collide in spectacular cosmic dances. Every photon of light from a quasar carries with it the signature of incredible violence and beauty combined. These objects represent some of the most extreme physics in the universe, where matter is heated to millions of degrees, where magnetic fields stronger than anything we can create on Earth twist and writhe through space, and where the very fabric of space-time itself is warped beyond recognition. They're nature's most powerful particle accelerators, cosmic engines that dwarf anything human technology could ever hope to achieve. But here's what makes quasars truly remarkable. They're not just random explosions in space. They're connected to the very story of how galaxies grow, how black holes form, and how the universe itself evolved from a simple, smooth soup of hydrogen and helium into the complex cosmic web of structures we see today. Each quasar is a chapter in that story, a snapshot of a moment when the universe was undergoing some of its most dramatic transformations. The first quasars were discovered almost by accident in the 1950s and 60s, when radio astronomers started picking up strange signals from what looked like ordinary stars. But these weren't stars at all. They were something far more exotic, something that challenged everything astronomers thought they knew about the universe. The mystery deepened when scientists realized these objects were moving away from us at incredible speeds, some at more than 90% the speed of light. This meant they had to be incredibly far away, and if they were that far away and we could still see them, they had to be unimaginably bright. For decades, quasars remained one of astronomy's greatest puzzles. How could something so small produce so much energy? How could these objects exist at such enormous distances? And why did they seem to be more common in the distant past than they are today? The answers to these questions would revolutionize our understanding of black holes, galaxy formation, and the evolution of the universe itself. Today, we know that quasars are powered by supermassive black holes, monsters millions or even billions of times more massive than our Sun. But that knowledge only leads to more questions. How did these black holes grow so large so quickly? What role do they play in shaping the galaxies around them? And what can they tell us about the fundamental nature of space, time, and matter itself? Think about this for a moment. When you look up at the night sky, you're seeing stars as they were years ago because light takes time to travel. The nearest star beyond our Sun is over 4 light years away, so you're seeing it as it was 4 years in the past. Now imagine looking at an object so distant that its light has been traveling for over 13 billion years. That light began its journey when the universe was just a cosmic infant, barely 700 million years old. The atoms in your body, forged in the hearts of ancient stars, didn't even exist yet when that light began its epic journey across space. This is the true magic of quasars. They allow us to be cosmic archaeologists, digging not through rock and soil, but through time itself. Each quasar observation is like opening a time capsule from the early universe, revealing secrets about cosmic evolution that we could never learn any other way. They show us what galaxies looked like when they were young and actively growing. They reveal the presence of supermassive black holes that somehow formed incredibly quickly after the Big Bang. And they trace the cosmic web of dark matter that connects everything in the universe. But quasars don't just tell us about the past. They're actively shaping the present and future of cosmic evolution. The energy they pump out influences star formation across entire galaxies. Their jets and winds can trigger the birth of new stars in some regions, while completely shutting down star formation in others. They're cosmic gardeners, pruning and shaping the growth of galaxies across billions of years. Perhaps most remarkably, quasars might hold clues to some of the deepest questions in physics. Do the fundamental constants of nature change over time? Is our understanding of gravity complete, or are there modifications needed when we deal with the most extreme environments in the universe? Can black holes actually destroy information, or is it preserved in ways we don't yet understand? Quasars, with their extreme physics and ancient light, might help us answer these profound questions. Tonight, we're going to decode that message and discover what quasars are really trying to tell us about the deepest mysteries of existence itself. We'll journey back in time to witness the birth of the most massive black holes in the universe. We'll explore how these cosmic monsters shaped the galaxies around them. And we'll discover how studying these distant beacons is helping us understand nothing less than the ultimate fate of everything that exists. The story of quasars is really the story of us, written in letters of light across the cosmic darkness. Welcome to the universe's greatest light show. The story of quasars begins with a mystery that baffled astronomers for decades. In the 1950s, radio telescopes started picking up powerful signals from space. These weren't the gentle whispers that most cosmic objects send our way. These were radio screams, incredibly loud broadcasts that seemed to be coming from points of light that looked like ordinary stars through optical telescopes. The term quasar comes from quasi-stellar radio source, a name that perfectly captured the confusion of those early discoveries. Here were objects that looked like stars but behaved like nothing astronomers had ever seen before. They were pumping out radio waves with the intensity of entire galaxies, yet they appeared as tiny pinpoints of light in even the most powerful telescopes of the time. The breakthrough came in 1963, when astronomer Martin Schmidt was studying the spectrum of light from an object called 3C273. Spectra are like cosmic fingerprints, revealing the chemical composition and physical conditions of distant objects. But the spectrum of 3C273 made no sense. The familiar lines of hydrogen that astronomers expected to see were nowhere to be found. Instead, there were mysterious lines at wavelengths that didn't match any known element. Then Schmidt had a brilliant insight. What if those weren't mysterious elements at all? What if they were ordinary hydrogen lines that had been shifted to much longer wavelengths by the expansion of the universe? This redshift effect happens when objects are moving away from us at tremendous speeds. The faster they move, the more their light gets stretched toward the red end of the spectrum. When Schmidt calculated how fast 3C273 would have to be moving to produce such a dramatic redshift, the answer was shocking. This object was racing away from us at nearly 16% the speed of light. In the context of an expanding universe, this meant it had to be incredibly far away, over 2 billion light-years from Earth. But here's where things got really mind-bending. If 3C273 was that far away and we could still see it clearly, it had to be producing an almost unimaginable amount of light. We're talking about an object that was outshining entire galaxies containing hundreds of billions of stars, yet it appeared to be no larger than a single star. This discovery opened the floodgates. Astronomers began finding more and more of these quasi-stellar objects, each one more distant and more luminous than the last. Some were so far away that their light had been traveling for over 10 billion years to reach us. We were seeing them as they existed when the universe was less than a quarter of its current age. The question that kept astronomers awake at night was simple but profound. What could possibly produce that much energy? The numbers were staggering. A typical bright quasar puts out more energy in a single second than our sun produces in 100,000 years. Some of the most luminous quasars shine with the power of 10 to the 14th suns. That's a 1, followed by 14 zeros worth of solar luminosities. For comparison, our entire Milky Way galaxy, with its 400 billion stars, produces only about 20 billion times the sun's luminosity. The brightest quasars are thousands of times more luminous than our entire galaxy. Yet all of this energy was somehow being produced in a region smaller than our solar system. Various theories were proposed to explain these cosmic powerhouses. Maybe they were massive stars in the process of collapsing. Maybe they were entire galaxies undergoing some kind of explosive transformation. Maybe they represented collisions between normal matter and antimatter. Each idea had problems, and none could fully explain the incredible energy output and compact size of quasars. The answer, when it finally came, was both elegant and terrifying. Quasars are powered by supermassive black holes, gravitational monsters millions to billions of times more massive than our sun. These aren't the stellar mass black holes formed when massive stars collapse. These are cosmic titans that somehow grew to enormous sizes in the early universe. But black holes themselves don't produce light. They're called black holes precisely because nothing, not even light, can escape their gravitational pull once it crosses the event horizon. So how can a black hole power the brightest objects in the universe? The answer lies not in the black hole itself, but in the swirling disk of matter that spirals into it. Picture a cosmic whirlpool with the black hole at its center. As gas, dust, and even entire stars fall toward the black hole, they form what astronomers call an accretion disk. This disk doesn't fall straight into the black hole. Instead, material spirals inward, getting compressed and heated to incredible temperatures by the immense gravitational forces and friction between particles. As matter in the accretion disk gets closer and closer to the black hole, it experiences tidal forces that stretch and compress it. The friction between different layers of the disk heats the material to temperatures of millions or even billions of degrees. At these temperatures, the matter glows brilliantly across the entire electromagnetic spectrum, from radio waves to X-rays. The efficiency of this process is remarkable. When hydrogen burns in the core of a star like our Sun, it converts about 0.7% of its mass into energy, according to Einstein's famous equation E equals mc squared. But when matter falls into a black hole's accretion disk, it can convert up to 42% of its mass into energy. This makes black hole accretion the most efficient energy production mechanism known in the universe. But the story doesn't end with the accretion disk. Many quasars also produce tremendous jets of material that shoot out from their poles at speeds approaching the speed of light. These jets are channeled by intense magnetic fields that thread through the accretion disk and around the black hole. The jets can extend for millions of light years into space, carrying energy and particles far beyond the host galaxy. These relativistic jets are responsible for much of the radio emission that first led to the discovery of quasars. When the high-speed particles in the jets interact with magnetic fields in space, they produce synchrotron radiation that glows brightly at radio wavelengths. Some jets are pointed almost directly at Earth, making their quasars appear even brighter due to relativistic beaming effects. We now know that quasars represent the most active phase in the life of supermassive black holes. They occur when these cosmic giants have an abundant supply of material to feed on, typically during galaxy mergers, or when gas-rich galaxies are still forming and growing. The host galaxies of quasars are often undergoing dramatic transformations, with star formation rates far above normal and signs of recent gravitational disturbances. The realization that quasars are powered by supermassive black holes revolutionized our understanding of galaxy evolution. We now know that nearly every large galaxy, including our own Milky Way, harbors a supermassive black hole at its center. Most of these black holes are currently quiet, having exhausted their local supply of fuel. But in the distant past, when the universe was younger and galaxies were actively growing and merging, many of these black holes went through quasar phases, shining brilliantly across the cosmos. This connection between quasars and galaxy evolution has profound implications. It suggests that supermassive black holes don't just passively sit at the centers of galaxies. Instead, they actively participate in galactic growth, regulating star formation through their powerful outflows and jets. The energy released by quasar activity can heat and disperse gas throughout a galaxy, temporarily shutting down star formation until the galaxy has time to cool and accumulate new material. Understanding what quasars really are has transformed them from mysterious cosmic oddities into crucial tools for studying the universe. They serve as beacons that illuminate the cosmic web of dark matter. They act as laboratories for studying physics under the most extreme conditions imaginable. And they provide windows into the early universe that would be impossible to achieve any other way. Today, we know of over 500,000 quasars, ranging from relatively nearby objects only a few hundred million light-years away, to ancient giants whose light has been traveling for over 13 billion years. Each one tells a unique story about cosmic evolution, black hole growth, and the complex interplay between gravity, magnetism, and matter in the most extreme environments the universe has to offer. The discovery that quasars are active galactic nuclei powered by supermassive black holes has opened up entirely new fields of astronomy. We can now study how these black holes form and grow over cosmic time. We can investigate the relationship between black hole mass and the properties of their host galaxies. And we can use quasars as probes of the intergalactic medium, the sparse gas that fills the space between galaxies. Modern telescopes have revealed that quasars come in many different varieties. Some are radio loud, producing powerful jets that can be detected by radio telescopes across the entire observable universe. Others are radio quiet, focusing most of their energy output into optical and ultraviolet light. Some quasars show dramatic variability, brightening and dimming on timescales of days or weeks as the accretion disk undergoes turbulent changes. Others remain relatively steady over decades of observation. The orientation of a quasar relative to Earth also affects how we see it. When we view a quasar face-on, looking directly down into the accretion disk, we see the full glory of its luminous output. But when we view it edge-on, the thick disk of gas and dust can partially obscure our view, making the same object appear much dimmer. Some quasars have jets pointed almost directly at us, creating blazars that appear incredibly bright due to relativistic effects that focus their emission in our direction. The study of quasar variability has revealed fascinating details about the structure of accretion disks. When the brightness of a quasar changes, different wavelengths of light respond at slightly different times. This time, lag tells us about the size and temperature structure of the accretion disk. The hottest, bluest light comes from the innermost regions near the black hole, while cooler, redder light originates from the outer parts of the disk. Perhaps most remarkably, astronomers have discovered that the mass of a galaxy's central supermassive black hole is closely correlated with properties of the galaxy itself, such as the velocity dispersion of stars in the galactic bulge. This suggests that black holes and their host galaxies grow together through some kind of feedback mechanism, with quasar activity playing a crucial role in regulating both processes. The feedback between quasars and their host galaxies works in both directions. Galaxy mergers can funnel gas toward the central black hole, triggering quasar activity. But the energy output from the quasar can also drive powerful winds that heat and disperse gas throughout the galaxy, temporarily shutting down both star formation and further black hole growth. This creates a self-regulating cycle that may explain why the most massive galaxies in the universe seem to have stopped forming new stars. The discovery of quasars also revolutionized our understanding of the early universe. Before quasars were found, astronomers had no way to study individual objects at distances greater than a few billion light-years. Quasars changed all that, providing bright beacons that can be seen across most of the observable universe. They've allowed us to study the universe when it was less than 1 billion years old, revealing a cosmos that was very different from what we see today. In those early times, galaxies were smaller and more gas-rich. Star formation rates were much higher than they are today, and the intergalactic medium was still in the process of being ionized by the first stars and quasars. Studying high redshift quasars has given us crucial insights into this cosmic dawn, when the universe was emerging from its dark age and beginning to light up with the first generation of luminous objects. The spectroscopy of distant quasars has also provided some of the best tests of fundamental physics over cosmic time. By comparing the ratios of different spectral lines in quasars at various redshifts, astronomers can search for possible changes in fundamental constants, like the fine structure constant or the proton-to-electron mass ratio. So far, these tests have shown that the laws of physics have remained remarkably constant over the past 13 billion years. Modern quasar surveys have found these objects in every corner of the sky, creating three-dimensional maps of supermassive black hole activity throughout cosmic history. These maps reveal the large-scale structure of the universe, tracing the cosmic web of dark matter filaments along which galaxies and quasars are distributed. They've also shown us that quasar activity peaked when the universe was about 3 billion years old and has been declining ever since as galaxies have exhausted their gas supplies. The study of quasars continues to push the boundaries of observational astronomy. The most distant quasars require the largest telescopes and most sensitive instruments to study in detail. Each new discovery extends our view further back in time, closer to the epoch when the first supermassive black holes were forming. These observations are helping us understand one of the most profound questions in cosmology. How did black holes, millions of times more massive than the Sun, manage to form so quickly after the Big Bang? As we've learned more about quasars, they've transformed from mysterious cosmic oddities into essential tools for understanding the universe. They serve as standard candles for measuring cosmic distances, as probes of the intergalactic medium, and as laboratories for studying physics under the most extreme conditions imaginable. Most importantly, they've shown us that the universe has always been a dynamic, evolving place, with dramatic episodes of growth and transformation that have shaped everything we see today. To understand just how bright quasars really are, we need to think about light in a completely different way than we're used to in everyday life. When we look at the brightest star in our night sky, Sirius, we're seeing an object that produces about 25 times more light than our Sun. That seems impressive until you realize that a typical bright quasar produces more light than 10 trillion stars like Sirius, all concentrated into a region smaller than our solar system. Let's put this in perspective with some cosmic comparisons that will truly blow your mind. Our Sun, which provides all the energy that powers life on Earth, has what astronomers call an absolute magnitude of about 4.8. This is a measure of how bright an object would appear if it were placed at a standard distance of about 32 light-years from Earth. A typical star like our Sun is pretty average in cosmic terms, neither particularly bright nor particularly dim. The brightest stars in our galaxy, massive blue supergiants like Rigel or Deneb, have absolute magnitudes around -7 or -8. These stellar giants pump out hundreds of thousands of times more light than our Sun. They're so luminous that they can be seen from thousands of light years away, serving as beacons that help astronomers map the structure of our galaxy. But even these stellar powerhouses pale in comparison to quasars. The absolute magnitude of a bright quasar can reach -30 or even brighter. To put this in perspective, that's 22 magnitudes brighter than our Sun. Since each magnitude represents a factor of about 2.5 in brightness, we're talking about an object that's roughly 10 to the 9th, or 1 billion times brighter than our Sun. Actually, let's be more precise about this, because the numbers are so staggering that they're worth getting exactly right. The brightest quasars have luminosities of up to 10 to the 14th power that of our Sun. That's 100 trillion solar luminosities. If you could somehow place such a quasar at the distance of our nearest stellar neighbor, Proxima Centauri, which is about 4 light-years away, it would appear in our sky as bright as the full moon. But that's not even the most mind-bending comparison. Our entire Milky Way galaxy, with its estimated 400 billion stars, has a total luminosity of only about 20 billion times that of our Sun. This means that the brightest quasars are roughly 5,000 times more luminous than our entire galaxy. Imagine that for a moment. A single object, no larger than our solar system, outshining 400 billion stars. To make this even more concrete, let's think about it in terms of energy output per second. Our Sun converts about 4 million tons of matter into pure energy every second, following Einstein's famous equation E equals mc². This produces about 3.8 times 10 to the 26th watts of power. It's an enormous amount of energy by human standards, enough to supply Earth's current energy needs for over 10 billion years in just 1 second. A bright quasar, by comparison, converts matter to energy at a rate that's 100 trillion times faster. We're talking about 400 billion tons of matter being converted to pure energy every single second. The amount of energy released by a quasar in 1 second equals what our Sun will produce over its entire 10 billion year lifetime. These numbers are so large that they strain human comprehension. To help visualize this, imagine that every person on Earth had their own personal Sun. That's about 8 billion suns total. Now imagine that each of those suns was somehow made 10,000 times brighter. The combined light output of all those enhanced suns would still be less than what a single bright quasar produces. The absolute magnitude scale that astronomers use is logarithmic, which means that small changes in magnitude correspond to huge changes in actual brightness. A quasar with an absolute magnitude of -30 is not just a little brighter than a star, with an absolute magnitude of -8. It's about 4 billion times brighter. This logarithmic scale is necessary because the range of luminosities in the universe is so enormous that a linear scale would be completely impractical. But quasars aren't just bright, invisible light. They're powerhouses across the entire electromagnetic spectrum. They produce intense radio waves that can be detected by telescopes thousands of light years away. They emit copious amounts of infrared radiation from heated dust in their host galaxies. They shine brilliantly in ultraviolet light that reveals the hottest regions of their accretion disks. And they produce high-energy X-rays and gamma rays from the most extreme physical processes occurring near their central black holes. This broad-spectrum emission is one of the key signatures that identifies an object as a quasar. Unlike stars, which have relatively simple spectra determined by their surface temperatures, Quasars show the complex signatures of multiple physical processes all occurring simultaneously. The radio emission comes from synchrotron radiation in their jets. The infrared light comes from dust heated by the intense radiation field. The optical and ultraviolet light comes from the hot accretion disk. And the X-rays come from the innermost regions where matter is being accelerated to nearly the speed of light, just before disappearing into the black hole. The fact that quasars are so bright across such a wide range of wavelengths makes them incredibly valuable for astronomical observations. Unlike most cosmic objects, which are bright in only a narrow range of the spectrum, quasars can be studied with radio telescopes, infrared telescopes, optical telescopes, ultraviolet satellites, and X-ray observatories. Each wavelength reveals different aspects of the physics occurring in and around these extraordinary objects. The brightness of quasars also varies with time, sometimes dramatically. Some quasars have been observed to double or triple their brightness in a matter of weeks, then fade back to their original luminosity over months or years. This variability tells us important things about the size and structure of the regions producing the light. Since information cannot travel faster than the speed of light, a quasar that varies significantly over a period of 1 year cannot be larger than 1 light year across. The fact that we see rapid variability in many quasars confirms that all this enormous energy output is indeed coming from a very compact region. The brightest quasars are so luminous that they can be seen from distances of over 13 billion light-years. This means we can observe them as they were when the universe was less than 1 billion years old. At such distances, even the Hubble Space Telescope can barely resolve the host galaxies surrounding these quasars. The quasar itself completely dominates the light from its entire galaxy, making it appear as a brilliant point source against the cosmic background. This extreme brightness has practical implications for how astronomers study quasars. While the intense luminosity makes them visible across vast distances, it also creates observational challenges. The bright quasar nucleus can completely overwhelm the much fainter light from its host galaxy, making it difficult to study how these objects fit into the broader context of galaxy evolution. Special techniques, like coronagraphs that block the bright central light, are needed to study the surrounding galactic environment. The record holders for absolute brightness among quasars are truly in a class of their own. Objects like APM 08279 plus 5255 with an absolute magnitude of -32.4, or the recently discovered quasar J0312-1806, shine with the luminosity of over 40 trillion suns. These hyperluminous quasars are thought to be powered by the most massive black holes in the universe, some containing over 10 billion times the mass of our Sun. To put the brightness of these record-breaking quasars in context, consider that the Andromeda Galaxy, our nearest large galactic neighbor, has a total luminosity of about 40 billion suns. The brightest quasars are therefore about 1,000 times more luminous than the entire Andromeda Galaxy. If such a quasar existed at the center of our local group of galaxies, it would dominate the sky, appearing as bright as Venus and visible even in broad daylight. The incredible brightness of quasars also allows astronomers to use them as cosmic flashlights, illuminating material along their line of sight that would otherwise be completely invisible. When quasar light passes through intervening gas clouds, it picks up absorption signatures that reveal the chemical composition, temperature, and density of that gas. This technique, called quasar absorption line spectroscopy, has revealed the presence of vast reservoirs of gas in the space between galaxies, gas that plays a crucial role in galaxy formation and evolution. Perhaps most remarkably, the brightness of quasars can tell us about the fundamental structure of space-time itself. When a massive object like a galaxy cluster lies between us and a distant quasar, Its gravitational field can bend and focus the quasar's light through an effect called gravitational lensing. This cosmic magnification can make already bright quasars appear even brighter, while also creating multiple images of the same object. By studying these gravitationally lensed quasars, astronomers can measure the distribution of dark matter in the universe and test Einstein's theory of general relativity under extreme conditions. The study of quasar brightness has also revealed important clues about cosmic evolution. By measuring the luminosity function of quasars, how many exist at different brightness levels, astronomers have discovered that the universe went through a golden age of quasar activity when it was about 3 billion years old. During this epoch, supermassive black holes were growing rapidly through accretion, producing the most luminous quasars ever observed. Since then, quasar activity has declined dramatically as galaxies have consumed most of their available gas supplies. Understanding the true brightness of quasars requires careful consideration of the effects of cosmic expansion and redshift. When we observe a distant quasar, its light has been stretched to longer wavelengths by the expansion of the universe. This means that what appears as visible light to us was actually emitted as higher energy ultraviolet radiation. Correcting for these effects is crucial for understanding the intrinsic properties of quasars and comparing objects at different distances. The brightness of quasars continues to amaze astronomers as new surveys discover ever more luminous examples. The upcoming Legacy Survey of Space and Time, to be conducted by the Vera Rubin Observatory, is expected to find millions of new quasars, including some that may break current brightness records. Each new discovery helps refine our understanding of how supermassive black holes grow and evolve, and how their enormous energy output shapes the cosmos around them. In the end, the incredible brightness of quasars serves as a testament to the raw power of gravity and the efficiency of black hole accretion. These cosmic lighthouses remind us that the universe contains phenomena far more extreme and energetic than anything we experience in our everyday lives. They represent the universe at its most dramatic and powerful, channeling the energy of matter, falling into gravitational oblivion, and broadcasting that energy across billions of light years of space and time. One of the most puzzling aspects of quasars is their distribution in space and time. When astronomers first began cataloging these mysterious objects in the 1960s and 70s, they noticed something strange. Almost all quasars seem to be incredibly distant. The nearest bright quasars are billions of light years away, while the most distant ones are over 13 billion light years from Earth. This immediately raised a profound question: why don't we see any quasars in our cosmic neighborhood? To understand this mystery, we need to think about what it means to look deep into space. When we observe distant objects in the universe, we're not just looking far away in space, we're also looking far back in time. Light travels at a finite speed, about 300,000 kilometers per second, which means it takes time to reach us from distant sources. When we look at a quasar 10 billion light years away, we're seeing it as it was 10 billion years ago, when the universe was less than a quarter of its current age. This relationship between distance and time is crucial to understanding quasar distribution. Most quasars are found at high redshifts, meaning they have Z values greater than 1. Redshift is a measure of how much the universe has expanded since the light left its source. A redshift of Z equals 1 means the universe has doubled in size during the light's journey. A redshift of Z equals 6, which characterizes some of the most distant quasars, means the universe has expanded by a factor of 7 since that light began its journey. The fact that most quasars are at high redshift tells us something profound about cosmic history. We're not seeing quasars primarily in the distant universe because that's where they happen to be located in space. We're seeing them there because that's when they were most active in cosmic time. The distant universe we observe represents the universe as it was billions of years ago. during an epoch when supermassive black holes were growing rapidly and shining as brilliant quasars. This epoch of intense quasar activity peaked when the universe was about 3 billion years old, corresponding to a redshift of around Z equals 2 to 3. During this cosmic era, the universe was a much more violent and active place than it is today. Galaxies were smaller, more gas-rich, and colliding with each other much more frequently. These conditions created the perfect environment for feeding supermassive black holes and triggering intense quasar activity. Think about it this way. If you could somehow travel back in time to visit the universe when it was 3 billion years old, you would see a cosmos ablaze with quasar activity. Brilliant points of light would be scattered across the sky, each one marking the location of a supermassive black hole in the process of devouring vast amounts of material. The night sky would be far more dramatic and energetic than anything we see today. But why were conditions so different back then? The answer lies in the process of cosmic evolution and structure formation. In the early universe, matter was distributed much more smoothly than it is today. Over billions of years, gravity has been at work, pulling matter together into increasingly complex structures. Small density fluctuations in the primordial universe grew into the first stars, then the first galaxies, then clusters of galaxies, and finally, the vast cosmic web of filaments and voids we see today. During the peak epoch of quasar activity, galaxies were still in the process of assembling. They were smaller and more numerous than today's galaxies, and they contained much larger reservoirs of gas that had not yet been converted into stars. This gas-rich environment was perfect for feeding supermassive black holes. When galaxies collided and merged, which happened much more frequently in the dense early universe, their gravitational interactions would funnel enormous amounts of gas toward their central black holes. These galactic mergers were like cosmic feeding frenzies for supermassive black holes. The gravitational disturbances would disrupt the normal rotation of gas in the galaxies, causing it to lose angular momentum and spiral inward toward the galactic center. As this gas accumulated around the central black hole, it would form the massive accretion disks that power quasar activity. The more violent the merger, the more gas would be funneled inward, and the brighter the resulting quasar would become. The frequency of galaxy mergers in the early universe was much higher than today for several reasons. First, the universe was smaller and denser, so galaxies were packed more closely together. Second, the dark matter halos that contain galaxies were still growing rapidly, capturing smaller neighboring galaxies through gravitational attraction. Third, the cosmic expansion rate was different in the early universe, allowing more time for gravitational interactions to play out before expansion could separate potentially merging systems. As the universe aged and expanded, several things changed that made intense quasar activity less common. Galaxies grew larger through mergers and began to exhaust their gas supplies through star formation. The rate of galaxy mergers decreased as cosmic expansion separated potential merger partners. And the intergalactic medium, the gas between galaxies, became hotter and more diffuse, making it harder for galaxies to accrete fresh supplies of fuel for their central black holes. This evolutionary picture explains why quasars become increasingly rare as we look at more recent cosmic epochs. In the local universe, corresponding to redshifts less than Z equals 0.5, bright quasars are extremely uncommon. The supermassive black holes that power them are still there, lurking at the centers of most large galaxies, but they've largely exhausted their local fuel supplies and entered a quiet phase of their evolution. Our own Milky Way galaxy provides a perfect example of this transition. At the center of our galaxy sits a supermassive black hole called Sagittarius A star, with a mass of about 4 million suns. This black hole is currently very quiet, accreting material at such a low rate that it produces only faint radio and X-ray emission. but evidence suggests that our galaxy went through episodes of much more intense activity in the past, when Sagittarius A* may have shone as a modest quasar. The Andromeda Galaxy, our nearest large galactic neighbor, also contains a quiet, supermassive black hole that was likely much more active in the past. In fact, nearly every large galaxy we can study in detail shows evidence of a central supermassive black hole that has gone through periods of intense activity, followed by long quiescent phases. The quasars we see in the distant universe are simply these same types of objects, caught during their active phases. This connection between cosmic evolution and quasar activity has profound implications for our understanding of galaxy formation. It suggests that the growth of supermassive black holes is intimately linked to the assembly of their host galaxies. The same processes that build up galactic mass also feed the central black holes, creating a co-evolutionary relationship that shapes both components over cosmic time. The decline in quasar activity since the peak epoch also explains an important observational fact. The energy density of quasar radiation in the universe has decreased dramatically over the past 10 billion years. This declining quasar background has allowed the intergalactic medium to cool and become more transparent, creating the relatively quiet cosmic environment we see today. But quasar activity hasn't completely ceased in the modern universe. Astronomers do find examples of nearby quasars, usually triggered by ongoing galaxy mergers or by gas-rich galaxies that still have sufficient fuel to feed their central black holes. These local quasars are typically less luminous than their high redshift counterparts, reflecting the more limited gas supplies available in the modern universe. The Seyfert galaxies, named after astronomer Carl Seyfert, who first catalogued them in 1943, represent a class of nearby active galactic nuclei that may be the modern descendants of ancient quasars. These objects show many of the same spectral features as quasars, but are much less luminous, suggesting they're powered by the same basic mechanism operating at a much lower level. Recent observations have also revealed that some nearby galaxies can undergo brief episodes of increased activity when they encounter fresh supplies of gas. The galaxy IC 3425, for example, appears to be in the process of transitioning from a normal galaxy to an active galactic nucleus as it accretes gas from a companion galaxy. These observations provide important insights into how quasar activity can be triggered in the modern universe. The distribution of quasars in space and time also provides crucial constraints on models of supermassive black hole formation. The fact that we see very luminous quasars at redshifts greater than Z equals 6 means that supermassive black holes with masses of billions of suns already existed when the universe was less than 1 billion years old. This places strong constraints on how quickly these black holes must have grown from their initial seed masses. Understanding why quasars are predominantly found in the distant universe has also led to important insights about cosmic reionization. During the epoch of peak quasar activity, the intense ultraviolet radiation from these objects helped to ionize the hydrogen gas in the intergalactic medium, fundamentally changing the thermal and chemical state of the universe. This reionization process played a crucial role in allowing the first galaxies to form and grow by heating and dispersing primordial gas clouds. The evolution of quasar activity over cosmic time serves as a cosmic clock, marking different phases in the universe's development. The rise of quasar activity signals the epoch when the first supermassive black holes formed and began growing rapidly. The peak of quasar activity corresponds to the era of maximum galaxy merger rates and star formation activity, and the decline of quasar activity marks the transition to the modern universe, where most galaxies have settled into a more peaceful existence. Modern surveys are pushing the boundaries of quasar detection to ever higher redshifts, searching for the most distant examples that can tell us about the very earliest epochs of cosmic evolution. The discovery of quasars at redshifts greater than Z equals 7 has revealed supermassive black holes that formed when the universe was less than 800 million years old, providing unprecedented insights into the rapid growth of these cosmic giants. The question of why quasars are so far away ultimately comes down to the fact that we live in a universe that has evolved dramatically over cosmic time. The distant quasars we observe are not separate from the galaxies we see around us today. They are the same galaxies, captured during their youth when they were actively growing and their central black holes were feeding voraciously. The apparent absence of nearby bright quasars is not because they're located elsewhere in space, but because they represent a phase of cosmic evolution that has largely passed, leaving behind the quiet galaxies and dormant black holes that populate our local cosmic neighborhood today. This evolutionary perspective has revolutionized our understanding of cosmic history. Instead of seeing quasars as exotic objects that exist in some distant realm, we now recognize them as a natural phase in the life cycle of galaxies and their central black holes. Every large galaxy we see today, including our own Milky Way, likely went through a quasar phase during its youth. The supermassive black hole at our galactic center, Sagittarius A star, may have once shone as brilliantly as the distant quasars we observe today. The rarity of nearby quasars also tells us something important about the efficiency of cosmic evolution. The universe has been remarkably effective at converting the chaotic, gas-rich environment of the early cosmos into the more organized, star-dominated galaxies we see today. This transformation didn't happen all at once, but rather occurred over billions of years as galaxies gradually consumed their gas supplies and settled into more stable configurations. The study of quasar evolution has revealed distinct epochs in cosmic history, each characterized by different levels of activity and different physical processes. The very earliest quasars, observed at redshifts greater than Z equals 7, represent the first generation of supermassive black holes forming in the pristine universe. These objects provide crucial insights into how the first black hole seeds managed to grow so rapidly in such a short time. During the intermediate epoch, at redshifts between Z equals 2 and Z equals 4, quasar activity reached its peak intensity. This era coincides with the maximum rate of star formation in the universe, suggesting a deep connection between the processes that build stars and those that feed supermassive black holes. The galaxies hosting these quasars were undergoing rapid assembly, with frequent mergers bringing fresh supplies of gas to fuel both star formation and black hole growth. The transition period, occurring at redshifts between Z equals 1 and Z equals 2, marks the beginning of the decline in quasar activity. During this epoch, many galaxies began to exhaust their gas supplies, and the merger rate started to decrease as cosmic expansion separated potential merger partners. This transition period is crucial for understanding how galaxies evolved from their chaotic youth to their more peaceful middle age. The modern epoch, corresponding to redshifts less than Z equals 1, is characterized by predominantly quiet supermassive black holes and mature galaxy populations. However, this doesn't mean that all activity has ceased. Occasional galaxy interactions can still trigger episodes of enhanced activity, producing the lower luminosity active galactic nuclei we observe in the nearby universe. The environmental dependence of quasar activity provides another clue to their distribution in space and time. In the early universe, quasars were found in a wide variety of environments, from isolated regions to dense clusters of galaxies. However, the most luminous quasars tended to be located in moderately dense environments, where galaxy interactions were common, but not so frequent as to disrupt the accretion process completely. As the universe evolved, the environmental preferences of active galactic nuclei changed. In the modern universe, we find that radio-loud quasars, those with powerful jets, are preferentially located in massive elliptical galaxies at the centers of galaxy clusters. This suggests that the environment plays an important role in determining the type of activity that can be sustained by supermassive black holes. The decline in quasar activity over cosmic time has also been linked to changes in the cosmic web itself. In the early universe, the filaments of dark matter that connect galaxy clusters contained more gas and were more efficient at funneling material toward galaxies. As the universe expanded and cooled, these filaments became less effective at delivering fresh gas supplies, contributing to the overall decline in galaxy growth rates and quasar activity. Modern computational simulations of cosmic evolution have been crucial for understanding the connection between quasar activity and cosmic time. These simulations follow the growth of structure in the universe from shortly after the Big Bang to the present day, tracking how gas flows through the cosmic web and feeds into galaxies. The results show that the peak epoch of quasar activity is a natural consequence of the hierarchical assembly of cosmic structure. The simulations also reveal that quasar feedback plays a crucial role in shaping cosmic evolution. The energy output from quasars can heat gas throughout their host galaxies and even in the surrounding intergalactic medium. This feedback can temporarily shut down star formation and black hole growth, creating a self-regulating mechanism that helps explain why the most massive galaxies stopped forming stars billions of years ago. The study of quasar clustering, how these objects are distributed relative to each other and to other cosmic structures, has provided additional insights into their evolution. In the early universe, quasars were more strongly clustered than they are today, reflecting the denser environment in which they formed. This clustering evolution is consistent with models in which quasars trace the growth of the most massive dark matter halos over cosmic time. The chemical evolution of quasars also reflects the changing conditions in the universe over time. The earliest quasars show evidence of forming from relatively pristine gas with low abundances of heavy elements. Later quasars, however, show enrichment signatures indicating that they formed from gas that had been processed by previous generations of stars. This chemical evolution provides an independent confirmation of the cosmic timeline established through other means. The discovery of quasar absorption line systems has revealed another dimension to the question of why quasars are so far away. These absorption features, created when quasar light passes through intervening gas clouds, show that the intergalactic medium has evolved dramatically over cosmic time. In the early universe, this medium was denser and more clumpy, providing more opportunities for gas to be funneled into galaxies and their central black holes. As we look toward the future, astronomers are developing new techniques to search for the earliest quasars in the universe. The James Webb Space Telescope, with its unprecedented infrared sensitivity, is expected to discover quasars at redshifts greater than Z equals 10, pushing back the frontier of the observable universe. These observations will provide crucial insights into how the first supermassive black holes formed and began shaping their cosmic environment. The question of why quasars are predominantly found in the distant universe ultimately reflects one of the most fundamental aspects of cosmic evolution. The universe has a history. Unlike the static cosmos imagined by earlier generations of astronomers, we now know that the universe has undergone dramatic changes over its 13.8 billion year existence. The distribution of quasars in space and time serves as a fossil record of this cosmic evolution, preserving evidence of the violent and energetic processes that shaped the early universe. Understanding this evolutionary perspective has practical implications for astronomical observations. When astronomers design surveys to study quasars, they must account for the fact that different types of quasars are found at different cosmic epochs. Surveys optimized for finding nearby active galactic nuclei use different techniques and target different wavelengths than surveys designed to discover the most distant quasars. The rarity of nearby bright quasars also means that detailed studies of quasar physics often require observations of very distant objects. This creates significant observational challenges, as even the largest telescopes can barely resolve the structure of quasar-host galaxies at high redshift. Future extremely large telescopes, with apertures of 30 to 40 meters, will be needed to study the detailed properties of individual high redshift quasars. The evolutionary perspective on quasar distribution also has implications for our understanding of the future of the universe. As cosmic expansion continues to accelerate, galaxy merger rates will continue to decline, making quasar activity even rarer than it is today. In the far future, the universe may enter an era where bright quasars become extinct, leaving behind only the faint emission from slowly accreting supermassive black holes. In conclusion, the question of why quasars are so far away reveals one of the most profound insights of modern cosmology. We live in an evolving universe with a rich and complex history. The distant quasars we observe are not exotic objects existing in some remote corner of space, but rather familiar galaxies caught during their youth, when they were actively growing and their central black holes were feeding voraciously. Their apparent absence from our local cosmic neighborhood reflects not their spatial distribution, but rather the passage of cosmic time and the remarkable efficiency with which the universe has evolved from its chaotic beginnings to the more peaceful cosmos we inhabit today. Of all the remarkable properties of quasars, perhaps none is more profound than their ability to serve as cosmic time machines. When we observe a quasar 13 billion light-years away, we're not just seeing an object in space. We're witnessing events that occurred when the universe was barely 800 million years old. The light reaching our telescopes today began its journey across the cosmos before our solar system existed, before our galaxy had taken its current form, even before most of the heavy elements in our bodies had been forged in stellar cores. This temporal aspect of quasar observations transforms astronomy from a purely descriptive science into a form of cosmic archaeology. Every photon of quasar light carries with it information about the conditions that existed in the ancient universe. The spectrum of a distant quasar reveals not only the properties of the quasar itself, but also the state of all the material that light has encountered during its billion-year journey to Earth. Consider what this means for our understanding of cosmic evolution. The expansion rate of the universe has been changing over time, influenced by the competing effects of matter, which tries to slow the expansion through gravity, and dark energy, which appears to be accelerating it. By measuring the distances and redshifts of quasars at various cosmic epochs, astronomers can trace how this expansion rate has evolved, providing crucial constraints on the nature of dark energy and the ultimate fate of the universe. The technique works because quasars can serve as standard candles, objects whose intrinsic brightness we can determine through other means. While quasars themselves vary widely in luminosity, certain relationships between their properties allow astronomers to estimate their true brightness. For example, there appears to be a correlation between the luminosity of a quasar and the width of certain emission lines in its spectrum. By measuring these line widths, astronomers can estimate the quasar's intrinsic brightness and compare it to how bright it appears from Earth. This comparison between intrinsic and apparent brightness reveals the distance to the quasar, while its spectrum reveals its redshift. Plotting distance against redshift for quasars at many different cosmic epochs creates a cosmic distance ladder that traces the expansion history of the universe. This technique has provided some of the strongest evidence for the acceleration of cosmic expansion driven by dark energy. But quasars reveal far more than just the expansion rate of the universe. They also serve as cosmic lighthouses, illuminating the otherwise invisible material that lies between us and them. As quasar light travels through space, it encounters clouds of gas in the intergalactic medium. These encounters leave absorption signatures in the quasar spectrum, creating what astronomers call the Lyman alpha forest. The Lyman alpha forest appears as a series of absorption lines at specific wavelengths corresponding to hydrogen gas at various redshifts. Each absorption line represents a cloud of gas at a particular distance along the line of sight to the quasar. By studying these absorption features, astronomers can map the distribution of matter in the universe across cosmic time, revealing how the cosmic web of filaments and voids has evolved over billions of years. This technique has revealed that the intergalactic medium is far from empty. Instead, it contains a vast network of gas filaments that connect galaxies and galaxy clusters. These filaments, which make up the cosmic web, contain the majority of the normal matter in the universe. Without quasar absorption line studies, we would have no way to detect this material, as it's far too faint to observe directly. The chemical composition of these gas clouds also tells a remarkable story of cosmic evolution. In the early universe, the gas was composed almost entirely of hydrogen and helium, the primordial elements created during Big Bang nuclear synthesis. But as successive generations of stars formed, lived, and died, they enriched the intergalactic medium with heavier elements like carbon, nitrogen, oxygen, and iron. By studying absorption lines from these heavier elements in quasar spectra, astronomers can trace the chemical evolution of the universe over cosmic time. They can see how the abundance of heavy elements has increased over billions of years, and how these elements have been distributed throughout space by stellar winds, supernova explosions, and outflows from galaxies. Perhaps most remarkably, quasar absorption line studies have allowed astronomers to test whether the fundamental constants of physics have remained constant over cosmic time. The fine structure constant, which determines the strength of electromagnetic interactions, affects the precise wavelengths at which atoms absorb and emit light. By comparing the ratios of different absorption lines in high redshift quasar spectra to laboratory measurements, astronomers can search for possible changes in this fundamental constant over billions of years. So far, these tests have shown that the fundamental constants appear to be remarkably stable over cosmic time. Any changes, if they exist at all, must be incredibly small. This provides strong support for the idea that the laws of physics as we understand them have remained constant throughout the observable history of the universe. The time machine aspect of quasar observations becomes even more powerful when we consider the information they provide about galaxy formation and evolution. High redshift quasars are often found in the most massive galaxies of their era, making them excellent tracers of how the most extreme structures in the universe have grown over time. By studying the host galaxies of quasars at different redshifts, astronomers can trace how galactic properties have evolved. They can see how stellar masses have grown, how star formation rates have changed, how galaxy morphologies have developed, and how the relationship between galaxies and their central black holes has evolved over cosmic time. The correlation between black hole mass and galaxy properties that we observe in the local universe appears to have been established quite early in cosmic history. Even high redshift quasars show evidence for the same scaling relationships between black hole mass and galaxy velocity dispersion that characterize nearby galaxies. This suggests that the co-evolution of galaxies and their central black holes has been a fundamental process throughout cosmic history. Quasar studies have also revealed how the process of cosmic reionization unfolded. During the first few hundred million years after the Big Bang, the universe was filled with neutral hydrogen gas that absorbed ultraviolet radiation. But as the first stars and quasars began to shine, their intense radiation gradually ionized this gas, making the universe transparent to ultraviolet light. By studying quasars at progressively higher redshifts, astronomers can probe deeper into this reionization epoch. The spectra of the most distant quasars show absorption features that reveal the transition from a neutral to an ionized universe. These observations suggest that reionization was a complex process that occurred over several hundred million years, with different regions of the universe becoming ionized at different times. The study of quasar variability across cosmic time has revealed how accretion onto supermassive black holes has evolved over the history of the universe. In the early universe, quasars showed more dramatic variability, suggesting that black hole feeding was more chaotic and episodic. As the universe aged and gas supplies became more organized, quasar variability became more subdued, reflecting more stable accretion processes. This evolution in quasar behavior mirrors the broader evolution of the cosmic environment. In the early universe, galaxy mergers and interactions were more common, leading to more violent and irregular feeding of central black holes. As the universe expanded and galaxies became more isolated, accretion became more steady and predictable. The jets produced by quasars also serve as probes of cosmic evolution. These relativistic outflows can extend for millions of light years, carrying energy and momentum far from their source galaxies. By studying how jet properties have changed over cosmic time, astronomers can understand how quasar feedback has influenced galaxy evolution throughout cosmic history. In the early universe, quasar jets appeared to have been more powerful and more common, consistent with the idea that supermassive black holes were growing more rapidly during this epoch. These powerful jets could have had dramatic effects on their surrounding environments, heating intergalactic gas and regulating star formation across vast regions of space. The time machine aspect of quasar observations has also revealed important clues about the nature of dark matter. The gravitational effects of dark matter influence how light from distant quasars is bent and focused as it travels through space. By studying gravitational lensing of quasar light by intervening dark matter structures, astronomers can map the distribution of dark matter across cosmic time. These studies have shown that dark matter halos have grown hierarchically over cosmic history, with smaller structures merging to form larger ones. This hierarchical growth is exactly what is predicted by the Standard Model of cosmology, providing strong support for our understanding of how cosmic structure has evolved. Quasar observations have also provided insights into the early formation of supermassive black holes themselves. The discovery of billion solar mass black holes at redshifts greater than Z equals 7 means these objects formed when the universe was less than 800 million years old. This places severe constraints on black hole formation scenarios, requiring either very massive seed black holes or extremely rapid growth rates in the early universe. The chemical abundances measured in high redshift quasar spectra provide additional constraints on early black hole formation. The presence of heavy elements in these ancient objects indicates that at least one generation of massive stars had already formed, lived, and died by the time these quasars were active. This suggests a rapid sequence of star formation, stellar evolution, and black hole growth in the early universe. Modern surveys are pushing the time machine capabilities of quasar observations to ever greater extremes. The Sloan Digital Sky Survey and its successors have discovered quasars at redshifts approaching Z equals 7.5, corresponding to light that has been traveling for over 13 billion years. Each new discovery extends our view further back toward the Big Bang itself. The upcoming generation of extremely large telescopes promises to extend quasar observations even further back in time. The James Webb Space Telescope has already begun discovering quasars at redshifts greater than Z equals 10, while future ground-based telescopes may be able to detect quasars from the very first billion years of cosmic history. These observations will provide unprecedented insights into the epoch of first light, when the first stars and galaxies were forming and beginning to ionize the universe. They will reveal how quickly supermassive black holes could form and grow in the pristine environment of the early universe, and they will trace the chemical evolution of the cosmos from its primordial state to the complex, element-rich universe we see today. The time machine nature of quasar observations also has practical implications for understanding cosmic evolution models. By providing snapshots of the universe at many different epochs, quasars allow astronomers to test theoretical predictions about how cosmic structure should evolve over time. Any successful model of cosmic evolution must be able to explain not just the properties of the local universe, but also the observed evolution of quasar populations over cosmic history. Perhaps most profoundly, quasar observations as cosmic time machines remind us that astronomy is fundamentally a historical science. Unlike laboratory experiments that can be repeated, astronomical observations capture unique moments in cosmic history that can never be reproduced. Each distant quasar represents a fossil record of conditions that existed billions of years ago, preserved in the light that has traveled across the universe to reach us. In this sense, quasars serve as cosmic historians, recording the story of how the universe has evolved from its simple beginnings to the complex, structured cosmos we inhabit today. They reveal a universe that has undergone dramatic changes over its history, transitioning from a smooth, featureless state to one filled with galaxies, stars, planets, and ultimately life itself. Through their role as cosmic time machines, quasars allow us to witness this grand story of cosmic evolution unfold across the vast expanse of space and time. The discovery of quasars at extremely high redshifts has revealed one of the most profound puzzles in modern astrophysics. How did supermassive black holes manage to grow so incredibly large so quickly after the Big Bang? When astronomers observe quasars at redshifts greater than z=6, they're seeing supermassive black holes containing billions of times the mass of our Sun, existing when the universe was less than 1 billion years old. This presents a cosmic chicken and egg problem that challenges our understanding of how these gravitational giants could have formed and grown so rapidly in the early universe. To appreciate the magnitude of this puzzle, we need to understand the fundamental limits on how quickly black holes can grow. When a black hole accretes matter, the gravitational energy released heats the infalling material to such high temperatures that it radiates intensely across the electromagnetic spectrum. This radiation exerts an outward pressure that opposes the inward pull of gravity, creating what astronomers call the Eddington limit. The Eddington limit represents the maximum rate at which a black hole can steadily accrete matter without blowing away its own fuel supply. For a black hole accreting at this maximum rate, there's a direct relationship between its mass and its luminosity. A black hole with the mass of our Sun accreting at the Eddington limit would shine with the brightness of about 30,000 suns. A billion solar mass black hole would outshine entire galaxies, which is exactly what we observe in the brightest quasars. But here's where the timeline becomes problematic. Even if a black hole could somehow maintain Eddington limited accretion continuously, it would take hundreds of millions of years to grow from a stellar mass seed of a few dozen solar masses to the billions solar mass giants we observe in high redshift quasars. When we account for the fact that black holes likely experience periods of reduced accretion or complete starvation, the growth timescale becomes even longer. This timing problem becomes acute when we consider the cosmic timeline. The first stars in the universe probably didn't form until at least 100 to 200 million years after the Big Bang. These first-generation stars would have had to live out their entire lives, collapse to form stellar mass black holes, and then somehow grow by factors of millions or tens of millions, all within the first 800 million years of cosmic history. The challenge is not just the rapid growth required, but also the efficiency with which this growth must have occurred. Observations of high redshift quasars suggest that supermassive black holes were already well established and actively growing when the universe was very young. This implies that whatever process created these black holes was remarkably effective at channeling material toward them during the chaotic conditions of the early universe. Several competing theories have emerged to explain this rapid black hole growth, each with its own advantages and challenges. The most straightforward approach assumes that supermassive black holes grew from stellar mass seeds formed by the collapse of the first generation of massive stars. These population 3 stars, formed from the pristine hydrogen and helium left over from the Big Bang, could have been much more massive than stars forming today, potentially reaching hundreds of solar masses before collapsing. When such massive stars collapse, they could form black holes with initial masses of 50 to 100 solar masses, providing larger seeds than the 10 to 20 solar mass black holes typically formed by stellar collapse today. While this gives black hole growth a head start, it still requires sustained growth at or near the Eddington limit for hundreds of millions of years to reach the observed masses of high redshift quasars. An alternative scenario proposes that some supermassive black holes form through direct collapse, bypassing the stellar phase entirely. In this model, massive gas clouds in the early universe, with masses of 100,000 solar masses or more, could collapse directly into black holes without ever forming stars. This would create intermediate mass black hole seeds of 10,000 to 100,000 solar masses, significantly reducing the growth time required to reach supermassive scales. Direct collapse requires very specific conditions to occur. The gas cloud must be able to collapse without fragmenting into smaller pieces that would form individual stars. This typically requires the absence of heavy elements that would cool the gas and promote fragmentation, as well as a source of heating that keeps the gas warm enough to resist fragmentation while still allowing overall collapse. Recent theoretical models suggest that direct collapse could occur in regions where intense ultraviolet radiation from nearby stars or quasars heats hydrogen molecules, preventing them from cooling the gas efficiently. These conditions might have been relatively common in the dense environment of the early universe, where the first generation of massive stars and protoquasars were beginning to illuminate their surroundings. A third possibility involves primordial black holes, hypothetical objects that could have formed from density fluctuations in the very early universe, potentially even before the first stars formed. If such primordial black holes existed with masses ranging from thousands to millions of solar masses, they could provide ready-made seeds for supermassive black hole growth without requiring any stellar formation at all. However, the existence of primordial black holes in the mass range relevant for supermassive black hole formation remains speculative. While they're allowed by our current understanding of physics, we have no direct observational evidence for their existence, and their formation would require very specific conditions in the early universe that may not have been realized. Regardless of how the initial seeds formed, the rapid growth to supermassive scales requires sustained feeding at very high rates. This presents its own set of challenges, because efficient black hole growth requires not just the presence of gas, but also a mechanism to remove the angular momentum from that gas, so it can spiral inward rather than simply orbiting at large distances. In the modern universe, galaxy mergers are often invoked as triggers for enhanced black hole growth. When two galaxies collide, their gravitational interaction can disrupt the normal rotation of gas, causing it to lose angular momentum and flow toward the central regions, where it can feed supermassive black holes. The chaotic conditions during mergers can funnel enormous amounts of material toward black holes in relatively short periods. The early universe may have been ideally suited for this type of rapid black hole growth. Galaxies were smaller, more numerous, and more gas-rich than they are today. The overall density of the universe was much higher, leading to more frequent gravitational interactions between neighboring systems. These conditions could have created a sustained period of rapid black hole growth through repeated merger-driven feeding episodes. Recent computer simulations of galaxy formation in the early universe support this picture. These simulations show that the first galaxies experienced frequent mergers and interactions that efficiently funneled gas toward their central regions. The simulations suggest that under these conditions, black holes could indeed grow from intermediate mass seeds to supermassive scales within the observed timeframes. The simulations also reveal that black hole growth and galaxy formation are intimately connected processes. As black holes grow and become more luminous, their energy output begins to affect their surroundings, heating and potentially expelling gas from their host galaxies. This creates a feedback mechanism that can regulate both star formation and further black hole growth. This feedback process may explain another puzzling aspect of high redshift quasars. They appear to follow similar scaling relationships between black hole mass and galaxy properties as we observe in the local universe. Despite the dramatically different conditions in the early universe, quasars at high redshift show evidence for the same correlations between black hole mass and galactic velocity dispersion that characterize nearby galaxies. The establishment of these scaling relationships so early in cosmic history suggests that the co-evolution of black holes and galaxies was already well underway when the universe was less than 1 billion years old. This implies that the feedback mechanisms that regulate black hole and galaxy growth were operating efficiently even under the extreme conditions of the early universe. Observational studies of high redshift quasars have provided additional clues about rapid black hole growth. Many of these objects show evidence for supersonic outflows and powerful jets that carry energy and momentum far from the central black hole. These outflows are signatures of extremely rapid accretion, suggesting that high redshift quasars were indeed growing at rates close to or even exceeding the Eddington limit. The chemical composition of high redshift quasars also provides insights into their growth history. Many of these objects show enhanced abundances of certain heavy elements, particularly those produced by massive stars with short lifetimes. This suggests that their host galaxies experienced intense episodes of star formation that enriched the local environment with heavy elements before being incorporated into the growing black holes. The metallicity patterns observed in high redshift quasars are consistent with rapid chemical evolution driven by successive generations of massive stars. This supports scenarios in which black hole growth occurs in environments that are simultaneously undergoing vigorous star formation, providing both the gas needed for black hole accretion and the stellar feedback that enriches that gas with heavy elements. Recent observations with the James Webb Space Telescope have begun to reveal the host galaxies of some high redshift quasars in unprecedented detail. These observations show that many early quasars reside in compact, highly star-forming galaxies that appear to be in the process of rapid assembly. The combination of intense star formation and rapid black hole growth suggests a period of co-evolution that was even more dramatic than previously thought. The discovery of multiple quasars in close proximity at high redshift has also provided insights into black hole growth mechanisms. These quasar pairs, separated by distances of only a few 100,000 light-years, suggest that black hole growth occurred in over-dense regions of the early universe where mergers and interactions were particularly common. Some of these close quasar pairs may represent the early stages of what will eventually become binary supermassive black hole systems. When such systems eventually merge, they would produce gravitational waves detectable by future space-based gravitational wave observatories, providing another window into the growth history of supermassive black holes. The study of quasar absorption line systems has revealed that rapid black hole growth often occurs in concert with large-scale gas flows in and around galaxies. High redshift quasars frequently show evidence for both inflowing gas that feeds the central black hole and outflowing gas driven by the energy release from accretion. These complex gas dynamics are thought to play a crucial role in regulating the black hole growth process. The feedback between growing black holes and their environments appears to be particularly important for understanding why black hole growth eventually slows down. As black holes reach supermassive scales and begin shining as bright quasars, their energy output becomes capable of heating and dispersing gas throughout their host galaxies and even into the surrounding intergalactic medium. This quasar feedback can temporarily shut down both star formation and further black hole growth, creating a self-regulating mechanism that may explain why we don't observe black holes that are arbitrarily massive. The most massive black holes in the local universe, with masses of 10 to 20 billion solar masses, may represent systems that reached an equilibrium between accretion-driven growth and feedback-driven regulation. The future of black hole growth research lies in combining improved theoretical models with more detailed observations of high redshift quasars. The next generation of extremely large telescopes will be able to resolve the host galaxies of distant quasars in much greater detail, revealing how black hole growth is connected to the assembly of galactic structure. Gravitational wave astronomy also promises to provide new insights into black hole growth by detecting the mergers of supermassive black hole pairs. These mergers represent the final stage of black hole growth through galactic interactions, and their detection will allow astronomers to directly measure the masses and spins of merging black holes across cosmic time. Perhaps most importantly, the study of rapid black hole growth in the early universe continues to reveal fundamental connections between the smallest and largest scales in astrophysics. The growth of supermassive black holes depends on atomic and molecular processes that determine how gas cools and condenses, stellar evolution processes that determine how the first stars form and die, and cosmological processes that determine how the first structures assemble in an expanding universe. Understanding how supermassive black holes manage to grow so quickly in the early universe ultimately requires understanding how all these processes work together in the extreme environment of the young cosmos. The quasars we observe at high redshift are the end result of this complex interplay, shining across billions of light years as beacons that illuminate one of the most remarkable chapters in the story of cosmic evolution. One of the most tantalizing possibilities in modern cosmology is the prospect of using quasars as standard candles for measuring cosmic distances. Standard candles are objects whose intrinsic brightness can be determined independently of their distance, allowing astronomers to calculate how far away they are by comparing their true luminosity to how bright they appear from Earth. This technique has been revolutionary for cosmology, with type Ia supernovae serving as the primary standard candles that led to the discovery of dark energy and the accelerating expansion of the universe. The appeal of developing quasars as standard candles lies in their unique advantages over other distance indicators. Unlike supernovae, which are transient events that fade away within months, quasars can be observed continuously over long periods, allowing for detailed studies of their properties. More importantly, quasars are visible across much greater distances than any other standard candle, potentially extending precise distance measurements to redshifts where no other technique is currently feasible. Type Ia supernovae, the current gold standard for cosmological distance measurements, can be observed reliably out to redshifts of about 1.5, corresponding to a time when the universe was roughly 4 billion years old. Beyond this distance, even the brightest supernovae become too faint for detailed spectroscopic study with current telescopes. Quasars, however, can be observed easily at redshifts of 6 or 7, and the most luminous examples are detectable even at redshifts approaching 8 or 9. This extended reach would allow astronomers to trace the expansion history of the universe much deeper into the past than is currently possible. Such measurements could provide crucial insights into the early behavior of dark energy, the nature of the cosmic acceleration, and the validity of our current cosmological model across a much broader range of cosmic epochs. However, developing quasars as reliable standard candles presents significant challenges that researchers are only beginning to understand. Unlike type Ia supernovae, which are thought to result from a relatively uniform physical process, quasars show enormous diversity in their properties. They span more than 4 orders of magnitude in luminosity, exhibit complex time variability, and are powered by accretion processes that depend sensitively on local environmental conditions. The key to making progress lies in identifying relationships between observable quasar properties that can be used to standardize their luminosities. just as the peak brightness of Type Ia supernovae can be standardized using the width of their light curves and their color evolution. Researchers are searching for correlations between quasar properties that might allow their intrinsic luminosities to be determined from spectroscopic observations. One of the most promising approaches involves the relationship between quasar luminosity and the properties of their broad emission lines. These lines are produced in the broad line region, a zone of rapidly moving gas clouds orbiting close to the central black hole. The width of these emission lines is determined by the orbital velocities of the gas clouds, which in turn depend on the mass of the central black hole, according to Kepler's laws of orbital motion. The reverberation mapping technique has shown that there's a strong correlation between the luminosity of certain emission lines and the size of the broadline region. By combining this size information with measurements of the emission line widths, astronomers can estimate the mass of the central black hole. Since quasar luminosity is related to black hole mass through the physics of accretion, these measurements potentially provide a way to standardize quasar brightnesses. The specific relationship most commonly used is based on the connection between the luminosity of the magnesium-2 emission line at a wavelength of 2,798 angstroms and the size of the broad line region. This relationship, combined with measurements of the line width, allows astronomers to estimate what's called the virial black hole mass. The ratio of the observed quasar luminosity to this virial mass provides a measure of how efficiently the black hole is accreting material. If quasars could be standardized using this accretion efficiency parameter, they would become powerful cosmological tools. The technique works because quasars accreting at similar fractions of their maximum possible rate should have similar intrinsic luminosities, regardless of their black hole masses or redshifts. By measuring the emission line properties and calculating the implied accretion efficiency, astronomers could potentially determine the intrinsic luminosity of any quasar. Early studies using this approach have shown promising results. When quasars are selected to have similar accretion efficiencies, their luminosity scatter is significantly reduced compared to the raw population. This suggests that the technique is indeed identifying a physical property that correlates with intrinsic quasar brightness. However, significant challenges remain in turning this correlation into a precision cosmological tool. One major challenge is the complex physics of the broad line region itself. The assumption that these emission lines accurately trace the gravitational potential of the central black hole requires that the gas clouds are in purely gravitational orbits. In reality, the broad line region is likely influenced by radiation pressure, magnetic fields, and outflowing winds, all of which can affect the observed line widths in ways that aren't directly related to black hole mass. Recent theoretical work has shown that the structure and kinematics of the broad line region can vary significantly depending on the accretion rate, viewing angle, and evolutionary state of the quasar. These variations introduce systematic uncertainties into black hole mass estimates that could propagate into errors in distance measurements. Understanding and correcting for these effects remains an active area of research. Another challenge involves the selection effects inherent in quasar samples. The quasars bright enough to be used for cosmological studies represent only the most luminous tip of the quasar population. These objects may not be representative of quasars in general, and their extreme properties could introduce biases into the standardization relationships. Moreover, the observational requirements for measuring emission line properties mean that only certain types of quasars can be used, potentially missing important systematic effects. The time variability of quasars presents additional complications for their use as standard candles. Unlike supernovae, which follow predictable light curves, quasars can vary unpredictably on timescales ranging from days to years. This variability affects both the continuum luminosity and the emission line properties, introducing scatter into the standardization relationships that must be carefully accounted for. Recent studies have attempted to address this issue by focusing on quasars observed during relatively stable periods or by averaging measurements over multiple epochs to reduce the impact of short-term variability. However, these approaches require extensive monitoring campaigns that are observationally expensive and may not be feasible for large samples of distant quasars. Despite these challenges, several research groups have reported encouraging results using quasar standardization techniques. Studies using samples of hundreds to thousands of quasars have found that the luminosity scatter can be reduced to levels approaching 20 to 30%, which, while larger than the few percent precision achieved with Type Ia supernovae, is still sufficient for meaningful cosmological constraints. These studies have generally found cosmological parameters consistent with those derived from other methods, providing some confidence that the quasar standardization approach is capturing real physical relationships rather than spurious correlations. However, the systematic uncertainties remain large enough that quasars are not yet competitive with other cosmological probes for precision measurements of parameters like the Hubble constant or the dark energy equation of state. One area where quasar standard candles could have immediate impact is in extending distance measurements to very high redshifts where other techniques are not applicable. Even with relatively large uncertainties, quasar distance measurements at redshifts greater than 2 could provide valuable constraints on the early evolution of dark energy and test whether the cosmological constant model remains valid across the full observable history of the universe. The development of improved standardization techniques remains an active area of research. Some studies have explored using multiple emission lines simultaneously to better constrain black hole masses and accretion rates. Others have investigated correlations between quasar properties and characteristics of their host galaxies that might provide additional standardization parameters. Machine learning approaches are also being applied to the problem, using large databases of quasar spectra to identify subtle correlations that might not be apparent from traditional analysis methods. These techniques have the potential to discover new standardization relationships or to improve the precision of existing ones by accounting for complex, multidimensional correlations between quasar properties. The observational requirements for quasar standard candle studies are driving the development of new astronomical surveys and analysis techniques. Large-scale spectroscopic surveys, like the Sloan Digital Sky Survey and its successors, are providing the statistical samples needed to test and refine standardization relationships. Future surveys planned for the next decade will observe quasars in much greater numbers and to much greater depths, potentially transforming our ability to use these objects for cosmological studies. The James Webb Space Telescope is opening up new possibilities for quasar cosmology by enabling detailed spectroscopic studies of much more distant quasars than were previously accessible. Its infrared sensitivity allows it to observe rest frame optical emission lines from quasars at very high redshifts, potentially extending standardization techniques to cosmic epochs that have never been probed before. Ground-based, extremely large telescopes currently under construction will provide complementary capabilities, offering the light-gathering power needed to obtain high-quality spectra of large numbers of quasars across wide areas of sky. These facilities will be crucial for building the statistical samples needed to understand and control systematic effects in quasar standardization. The theoretical understanding of quasar physics is also advancing rapidly, driven by improved computer simulations of black hole accretion and feedback processes. These simulations are providing new insights into the physical relationships that underlie potential standardization techniques and are helping to identify the conditions under which these relationships are most reliable. Recent simulations have shown that the emission line properties of quasars are indeed sensitive to black hole mass and accretion rate in ways that are broadly consistent with observational standardization attempts. However, they also reveal significant scatter and systematic variations that must be accounted for in any precision cosmological application. The ultimate goal of quasar standard candle research is to achieve precision comparable to that of Type Ia supernovae while extending to much greater distances. This would revolutionize our understanding of cosmic acceleration by providing detailed measurements of the expansion history across most of the observable universe. Such measurements could distinguish between different dark energy models and test whether general relativity remains valid on cosmic scales across all accessible redshifts. Progress toward this goal requires continued advances in both observational techniques and theoretical understanding. The observational challenges include obtaining larger, more complete samples of quasars with high-quality spectroscopic data, developing better methods for measuring emission line properties and controlling systematic effects, and understanding the selection biases inherent in quasar surveys. The theoretical challenges involve improving our understanding of the physics of black hole accretion, the structure and dynamics of the broad line region, and the relationship between quasars and their host galaxies. Success in meeting these challenges could make quasars one of the most powerful tools in cosmology, extending our ability to probe the universe's expansion history deeper into the past than any other currently available technique. Even if quasars never achieve the precision of supernovae as standard candles, they may still prove valuable as complementary distance indicators that can cross-check results from other methods and provide measurements in previously inaccessible redshift ranges. The development of multiple independent approaches to measuring cosmic distances is crucial for building confidence in our understanding of cosmic acceleration and testing the foundations of modern cosmology. The story of quasars as potential standard candles illustrates the ongoing evolution of observational cosmology, where new types of objects and novel analysis techniques continually expand our ability to probe the fundamental properties of the universe. Whether or not quasars ultimately achieve their promise as precision distance indicators, the research aimed at developing them as standard candles is advancing our understanding of both quasar physics and cosmological methodology in ways that will benefit astronomy for years to come. The relationship between quasars and their host galaxies represents one of the most profound connections in astrophysics, linking the smallest and largest scales of cosmic structure in ways that fundamentally shape the evolution of the universe. For decades after their discovery, quasars were studied primarily as isolated point sources, brilliant beacons whose host galaxies were completely overwhelmed by the intense nuclear emission. Only with the development of sophisticated observational techniques and theoretical models have astronomers begun to understand that quasars and galaxies are not separate phenomena, but rather intimately connected components of a single evolutionary system. This connection operates through a complex web of feedback mechanisms that regulate both the growth of supermassive black holes and the formation of stars throughout their host galaxies. When a supermassive black hole enters its active quasar phase, the enormous energy output doesn't just make the object visible across cosmic distances. It fundamentally alters the physical conditions throughout the entire galaxy, heating gas, driving powerful outflows, and either triggering or suppressing star formation, depending on the specific circumstances. The story begins with the fuel that powers both processes, the cold gas that pervades galaxies and provides the raw material for both star formation and black hole accretion. In a typical galaxy, this gas settles into a rotating disk where it gradually cools and condenses to form new stars. However, the same gravitational forces that funnel gas towards star-forming regions can also channel material toward the central supermassive black hole, particularly during galaxy mergers or other gravitational disturbances. When large amounts of gas reach the central regions of a galaxy, several things can happen simultaneously. Some of the gas forms stars at an accelerated rate, creating what astronomers call a starburst. Other portions of the gas form an accretion disk around the central black hole, powering intense quasar activity. The energy released by both processes heats the surrounding gas, creating a complex interplay between star formation, black hole growth, and galactic gas dynamics. This interplay is far from peaceful. The energy output from an active quasar can reach levels that dwarf the combined luminosity of all the stars in its host galaxy. This energy couples to the surrounding gas through radiation pressure, shock heating, and the acceleration of charged particles in powerful jets and winds. The result is a dramatic transformation of the galactic environment that can either enhance or completely shut down star formation across vast regions of space. Observational evidence for this quasar-galaxy connection comes from multiple sources. Studies of nearby galaxies have revealed that virtually every large galaxy contains a supermassive black hole at its center, with the mass of that black hole closely correlated with properties of the galactic bulge, particularly the velocity dispersion of stars in the central regions. This tight correlation suggests that black holes and their host galaxies have grown together through some kind of feedback mechanism over cosmic time. The correlation is remarkably precise, spanning more than 3 orders of magnitude in black hole mass and holding for galaxies with very different histories and environments. The black hole mass is typically about 0.1% of the mass of the galactic bulge, a ratio that appears to be maintained regardless of whether the galaxy is a massive elliptical, a spiral like the Milky Way, or even a dwarf galaxy with a relatively small central bulge. This mass relationship implies that the growth of supermassive black holes is somehow regulated by the properties of their host galaxies, or vice versa. Since black holes represent such a tiny fraction of the total galactic mass, the most likely explanation is that black hole activity provides feedback that regulates galaxy formation and evolution. When black holes grow rapidly during quasar phases, their energy output affects the entire galaxy, creating a self-regulating system that maintains the observed mass correlations. The feedback mechanisms operate through several different channels, each affecting different scales and types of galactic structure. On the smaller scales, the intense radiation from the accretion disk can ionize and heat gas in the immediate vicinity of the black hole, creating a zone where star formation is completely suppressed. This radiative feedback is most important for lower mass black holes and moderate accretion rates, where the radiation pressure can effectively clear gas from the central regions without requiring extremely high energy outflows. For more massive black holes and higher accretion rates, mechanical feedback becomes dominant. The relativistic jets produced by many quasars carry enormous amounts of energy and momentum that can affect gas throughout the entire galaxy and even in the surrounding intergalactic medium. These jets can create shockwaves that heat gas to temperatures of millions of degrees, making it unable to cool and condense into new stars. The jets can also drive large-scale outflows that physically remove gas from the galaxy altogether. Observations of many quasars reveal broad absorption lines in their spectra, indicating that gas is flowing away from the central regions at speeds of thousands of kilometers per second. Some of these outflows are so powerful that they can expel gas at velocities approaching 1% of the speed of light, carrying away more material than the black hole is actually consuming. These outflows have been observed to extend far beyond the central regions of quasar host galaxies. In some cases, quasar-driven winds have been detected at distances of tens of thousands of light-years from the central black hole, affecting star formation across significant fractions of the host galaxy. The energy carried by these outflows is sufficient to completely halt star formation in the most massive galaxies, explaining why the most massive elliptical galaxies in the universe appear to have stopped forming new stars billions of years ago. The timing of quasar activity relative to galaxy formation provides additional insights into the connection between these processes. Observations of high redshift quasars show that many of them reside in galaxies that are undergoing intense episodes of star formation, with rates hundreds of times higher than in typical present-day galaxies. This suggests that quasar activity and rapid galaxy assembly often occur simultaneously, driven by the same underlying processes. Galaxy mergers appear to play a crucial role in triggering both phenomena. When two gas-rich galaxies collide, their gravitational interaction disrupts the normal rotation of gas in both systems, causing material to lose angular momentum and flow toward the central regions. This infalling gas simultaneously fuels enhanced star formation and feeds the central supermassive black holes, creating conditions for both starburst and quasar activity. Computer simulations of galaxy mergers have confirmed this picture, showing that major mergers between gas-rich galaxies can trigger episodes of intense quasar activity that last for tens to hundreds of millions of years. During these episodes, the central black holes can grow by factors of 10 or more, while the host galaxies convert large fractions of their gas into new stars. The energy output from both processes eventually becomes so intense that it drives away the remaining gas, terminating both star formation and black hole growth. This merger-driven scenario explains many observed properties of quasar-host galaxies, including their tendency to show morphological disturbances and enhanced star formation rates. It also explains why the peak epoch of quasar activity, occurring when the universe was about 3 billion years old, coincides with the era of maximum galaxy merger rates and cosmic star formation. However, not all quasar activity requires major galaxy mergers. Observations have identified numerous examples of quasars in galaxies that show no obvious signs of recent interactions. These objects may be powered by more gradual processes, such as the secular evolution of galactic disks or the accretion of gas from the intergalactic medium. Understanding the full range of processes that can trigger quasar activity remains an active area of research. The impact of quasar feedback on galaxy evolution extends beyond simply regulating star formation rates. The energy injection from quasar activity can fundamentally alter the structure and morphology of galaxies, potentially explaining the origin of some of the different galaxy types we observe today. For example, the powerful outflows from quasars may be responsible for inflating the extended gaseous halos observed around massive elliptical galaxies. Quasar feedback may also play a role in establishing the relationship between galaxies and their dark matter halos. The energy released during quasar activity can heat gas throughout the galaxy and even in the surrounding dark matter halo, affecting how efficiently the halo can capture additional gas from the intergalactic medium. This process, known as halo quenching, may explain why the most massive dark matter halos host galaxies that are less efficient at forming stars than their lower mass counterparts. The chemical evolution of galaxies is also influenced by quasar activity. The powerful outflows driven by quasar energy can transport heavy elements produced by stellar nucleosynthesis far from their sites of origin, distributing these elements throughout the galaxy and even into the intergalactic medium. This metal enrichment process affects subsequent generations of star formation and may explain the observed correlations between galaxy mass metallicity and star formation efficiency. Recent observations have begun to reveal the detailed structure of quasar outflows and their impact on galactic gas. Spectroscopic studies using facilities like the Atacama Large Millimeter Array have detected molecular gas outflows with velocities of hundreds of kilometers per second, carrying away gas that would otherwise form new stars. These observations provide direct evidence for the predicted feedback mechanisms and allow astronomers to measure their efficiency in real time. The discovery of dual quasars, systems containing two active supermassive black holes in the same galaxy, has provided additional insights into the connection between quasar activity and galaxy evolution. These systems are thought to represent galaxy mergers caught in the act, with both central black holes simultaneously accreting material during the final stages of the merger process. Studies of dual quasars reveal how quasar activity evolves during galaxy interactions. and how the eventual merger of the black holes affects the resulting galaxy. The host galaxies of quasars also show distinctive properties that distinguish them from normal galaxies at the same cosmic epoch. Many quasar hosts have disturbed morphologies, enhanced star formation rates, and unusual gas distributions that reflect the violent processes occurring during episodes of rapid black hole growth. These properties provide important clues about the conditions that trigger quasar activity and the impact of that activity on galactic structure. As quasars evolve and their activity declines, their host galaxies undergo a transition to a more quiescent state. The powerful outflows that characterize active quasars gradually weaken as the fuel supply diminishes, allowing gas to settle back into more stable configurations. However, the impact of the quasar phase leaves lasting signatures in the galaxy's structure, stellar populations, and chemical composition. The modern universe contains numerous examples of galaxies that appear to be the evolved descendants of ancient quasar hosts. These post-quasar galaxies often show evidence for past episodes of intense activity, including disturbed stellar distributions, unusual chemical abundance patterns, and the presence of dormant supermassive black holes that are much more massive than would be expected based on current galactic properties. Understanding the quasar-galaxy connection has important implications for models of cosmic evolution. The feedback mechanisms that link black hole growth to galaxy formation help explain why the universe evolved from a chaotic, gas-rich state in its youth to the more organized, star-dominated cosmos we see today. Without this feedback, galaxies would likely have converted much larger fractions of their gas into stars, leading to a very different cosmic environment. The connection between quasars and galaxies also provides insights into the nature of dark matter and dark energy. The efficiency of quasar feedback depends on the properties of dark matter halos and the cosmic expansion rate, making quasar observations sensitive probes of these fundamental components of the universe. Future surveys that study large samples of quasars and their host galaxies will provide new constraints on cosmological models and tests of our understanding of structure formation. Perhaps most importantly, the quasar-galaxy connection demonstrates that the universe is a deeply interconnected system where phenomena occurring on vastly different scales influence each other in profound ways. The growth of supermassive black holes, which operate on scales comparable to our solar system, can affect the evolution of entire galaxies spanning hundreds of thousands of light years. This connection illustrates the fundamental unity of astrophysical processes and the importance of understanding cosmic evolution as a coherent, integrated story, rather than a collection of separate phenomena. The story of the quasar-galaxy connection continues to evolve as new observations and theoretical models reveal additional layers of complexity in this relationship. Each new discovery adds to our understanding of how the most extreme objects in the universe have shaped the cosmic environment that we inhabit today, connecting the distant, brilliant quasars we observe across billions of light years to the quiet galaxies that populate our local cosmic neighborhood. Quasars are more than cosmic fireworks. They're signposts. They tell us that the universe was already complex less than 1 billion years after the Big Bang. They trace the growth of the largest black holes, map the structure of matter across billions of light years, and may even hint if the laws of physics have shifted over time. When we step back and consider everything we've learned about quasars, a profound story emerges. These brilliant beacons are messengers from the universe's youth, carrying information across vast stretches of space and time about epochs and processes that would otherwise remain forever hidden from us. Each quasar observation is like receiving a letter from the ancient cosmos, written in the language of light and decoded through the careful analysis of spectra and images. The first message quasars bring us is one of rapid cosmic evolution. the mere existence of supermassive black holes containing billions of solar masses, when the universe was less than 800 million years old, tells us that the early cosmos was far from the simple, uniform state we might naively expect. Instead, it was a dynamic environment where enormous structures could assemble with remarkable speed through processes we're only beginning to understand. This message challenges our understanding of how cosmic structure forms and evolves. The standard model of cosmology, built around the gravitational collapse of dark matter and the hierarchical assembly of cosmic structure, struggles to explain how such massive black holes could have formed so quickly. The existence of high redshift quasars forces us to consider exotic formation mechanisms, extreme accretion rates, or perhaps modifications to our understanding of the early universe itself. Quasars also tell us about the intimate connection between small-scale and large-scale physics in the universe. The growth of supermassive black holes, occurring on scales comparable to our solar system, is intimately linked to the formation and evolution of galaxies spanning hundreds of thousands of light years. This connection operates through feedback mechanisms that regulate both star formation and black hole growth, creating a cosmic ecosystem where the smallest and largest structures influence each other across vast differences in scale. This message has profound implications for our understanding of cosmic evolution. It suggests that the universe is not simply a collection of independent objects evolving in isolation, but rather a deeply interconnected system where phenomena occurring in one location can influence processes across enormous distances. The energy released by quasar activity can affect gas throughout entire galaxies and even in the surrounding intergalactic medium, shaping the cosmic environment on scales far larger than the black holes themselves. Perhaps most remarkably, quasars serve as cosmic time machines that allow us to study the universe's history in unprecedented detail. When we observe a quasar at redshift 6, we're seeing it as it existed when the universe was only about 900 million years old. The light reaching our telescopes today began its journey before our solar system existed, carrying with it information about cosmic conditions that existed in the distant past. This temporal dimension of quasar observations transforms them into archaeological tools that reveal how the universe has changed over billions of years. By studying quasars at different redshifts, astronomers can trace the evolution of cosmic structure, the chemical enrichment of the universe, the reionization of intergalactic gas, and the changing rate of cosmic expansion. Each observation adds another data point to our understanding of cosmic history. The chemical message carried by quasars is particularly profound. The spectra of distant quasars reveal the presence of heavy elements that could only have been produced by stellar nucleosynthesis. This tells us that even in the very early universe, at least one generation of massive stars had already formed, lived out their brief lives, and exploded as supernovae, enriching their surroundings with the products of nuclear fusion. This chemical evolution story, written in the absorption and emission lines of quasar spectra, traces how the universe transformed from its initial state of pure hydrogen and helium to the chemically complex environment we see today. The gradual increase in heavy element abundances over cosmic time reflects the cumulative effect of stellar evolution, revealing how successive generations of stars have built up the periodic table of elements that makes complex chemistry and ultimately life possible. Quasars also carry messages about the large-scale structure of the universe itself. The cosmic web of dark matter filaments that connects galaxies and galaxy clusters is largely invisible to direct observation, but its presence can be inferred from the absorption signatures it creates in quasar light. As photons travel from distant quasars to Earth, they encounter gas clouds associated with this cosmic web, creating absorption features that map the distribution of matter across cosmic time. This technique, known as quasar absorption line spectroscopy, has revealed that the intergalactic medium is far from empty. Instead, it contains a vast network of gas filaments that trace the underlying dark matter structure. By studying how these absorption systems evolve with cosmic time, astronomers can understand how the cosmic web has grown and changed over the history of the universe. The message about cosmic expansion carried by quasars is potentially revolutionary for our understanding of dark energy and the ultimate fate of the universe. If quasars can be developed as reliable standard candles, they could extend precise distance measurements to redshifts where no other technique is currently applicable. This would allow astronomers to trace the expansion history of the universe much deeper into the past than is currently possible with Type Ia supernovae. Such measurements could reveal whether dark energy has remained constant over cosmic time or has evolved in ways that might distinguish between different theoretical models. They could also test whether Einstein's theory of general relativity remains valid on cosmic scales across the full observable history of the universe. The stakes are enormous, as any deviation from our current understanding could point toward new physics beyond the standard model of cosmology. Perhaps most intriguingly, quasars may be telling us about the fundamental constants of nature themselves. The precise wavelengths at which atoms absorb and emit light depend on constants like the fine structure constant, which determines the strength of electromagnetic interactions. By comparing absorption line ratios in high redshift quasar spectra to laboratory measurements, astronomers can search for possible changes in these fundamental constants over cosmic time. So far, these tests have shown that the fundamental constants appear remarkably stable over billions of years, providing strong support for the idea that the laws of physics, as we understand them, have remained unchanged throughout the observable history of the universe. However, the precision of these measurements continues to improve, and any future detection of variations could revolutionize our understanding of the deepest principles governing physical reality. The message about cosmic reionization carried by quasars is crucial for understanding one of the most important phase transitions in cosmic history. During the first few 100 million years after the Big Bang, the universe was filled with neutral hydrogen that absorbed ultraviolet radiation. The first stars and quasars gradually ionized this gas, making the universe transparent and allowing light to travel freely across cosmic distances. Quasars at the highest observable redshifts provide direct probes of this reionization process. Their spectra show absorption features that reveal the transition from a neutral to an ionized universe, providing crucial constraints on when and how this cosmic phase transition occurred. Understanding reionization is essential for comprehending how the first galaxies formed and how they began to influence their cosmic environment. The environmental message carried by quasars reveals how cosmic evolution has been shaped by feedback between different scales and different physical processes. The energy released by quasar activity doesn't just make these objects visible across vast distances. It fundamentally alters the conditions for galaxy formation and star formation throughout the universe, creating a complex web of cause and effect that has shaped cosmic evolution over billions of years. This feedback operates in both directions. Galaxy mergers and interactions can trigger quasar activity by funneling gas towards central supermassive black holes. But the resulting energy release can then affect star formation throughout the host galaxy and even in neighboring systems. This creates a complex evolutionary story where galaxies and their central black holes grow together through a series of feeding and feedback cycles. The demographic message revealed by quasar surveys tells us about the statistical properties of cosmic evolution. By studying how the number density and luminosity distribution of quasars has changed over cosmic time, astronomers can understand how the universe transitioned from its chaotic youth to the more organized cosmos we see today. The peak of quasar activity, occurring when the universe was about 3 billion years old, marks a crucial epoch in cosmic history. when galaxy formation and black hole growth were at their most intense. This demographic evolution reflects deeper changes in cosmic conditions. The early universe was denser, more gas-rich, and more conducive to violent processes like galaxy mergers and rapid black hole growth. As the universe expanded and evolved, these conditions became less common, leading to the decline in quasar activity that we observe in more recent cosmic epochs. Quasars also carry messages about the nature of extreme physics in the universe. The conditions near supermassive black holes represent some of the most extreme environments that exist, with gravitational fields so strong that they warp space-time itself, magnetic fields billions of times stronger than Earth's, and matter accelerated to velocities approaching the speed of light. Studying these extreme conditions provides tests of our understanding of physics under circumstances that can never be replicated in terrestrial laboratories. The relativistic jets produced by many quasars serve as natural particle accelerators that dwarf anything humans have built. These jets accelerate particles to energies far beyond what's achievable with current technology, providing insights into high-energy physics that complement studies conducted with artificial accelerators. The radiation produced by these jets spans the entire electromagnetic spectrum, from radio waves to gamma rays, revealing the complex physics of magnetic field acceleration and synchrotron emission. Perhaps most profoundly, quasars tell us about the unity of cosmic evolution. The story they reveal is not one of isolated objects evolving independently, but rather of a deeply interconnected universe where phenomena occurring on vastly different scales influence each other in fundamental ways. The formation of the first stars affects the chemistry of the intergalactic medium. Galaxy mergers trigger quasar activity. Quasar feedback regulates star formation. Black hole growth correlates with galaxy properties. This interconnectedness suggests that understanding any aspect of cosmic evolution requires understanding the whole system. Quasars serve as key nodes in this cosmic web of relationships, linking processes occurring on scales from stellar masses to cosmic horizons. They remind us that the universe is not just a collection of objects in space, but a single, evolving system with a coherent history and an uncertain future. The message that emerges from decades of quasar research is ultimately one of cosmic complexity and beauty. These brilliant beacons reveal a universe that is far richer and more intricate than we could have imagined when they were first discovered. They show us a cosmos where the smallest scales affect the largest, where the past shapes the present, and where extreme physics creates the most beautiful and powerful phenomena we can observe. As we continue to study quasars with ever more sophisticated instruments and techniques, their messages become clearer and more detailed. Each new observation adds to our understanding of cosmic evolution and our place within it. The distant quasars we see today are not separate from our own cosmic environment. They are part of the same evolutionary story that led to the formation of our galaxy, our solar system, and ultimately ourselves. In the end, what quasars are trying to tell us is nothing less than the story of cosmic evolution itself, written in letters of light across the vast darkness of space and time.